Okay, good morning. This is a video lecture on electric field. So we are done with electrostatics, which is about the interaction between charges. Next will be about the field surrounding a certain electric charge. So basically, electric field is just like gravitational forces or gravitational field. So let us say our planet is here, and what surrounds a planet is a gravitational field. And if a certain massive object or an object having a certain mass is within the gravitational field of that planet, or in our case, our Earth, so that object will be acted upon by gravitational forces. In other words, anything that is within the gravitational field of Earth will experience a gravitational force. Same way as with electric charges. So if you have a certain charge, let us say a proton, surrounding a proton is what we call an electric field. So any other charged particle within that field will be acted by a certain electric force. So anything or any charged object could feel a force of either attractive force or a repulsive force if it is within the electric field of a certain charged object. So electric field is like an energetic aura that extends through space. So they are somewhat similar to gravitational field, where gravitational force exists within that field, and electric field, where there is an electric force that exists within that field, as long as there is, or as long as the another electric charge is within that field. So sometimes we call it a force field. Force field because there's a force that exists as any other massive object in the case of gravitational field, or as any other electric charge that that is within that field. So it's a force field. So anything could feel a force around or within that field. So electric field has both magnitude and direction. So meaning it has a numerical value. At the same time, it has to have a direction. So the magnitude of the field at any point is simply the force per unit charge. So we have here the force per unit charge. So at a certain electric field, for example, at this point, a another electric charge would feel a force at this particular distance. So another charge would feel a force. So that is the force per the charge of the that charge particle that is coming near a certain charge particle. So this charge particle right here would feel a force. So this charge particle right here would feel a force at that particular location. You follow? So the greater is the force, the greater also is the electric field. So if you look at it here, so we have here, if you observe the arrows from from a shorter arrow to a longer arrow, and near to the electric charge is, the force is the greatest. So the greater is the force, the greater is the intensity of the electric field. And for convention, for convention, um, what the electric field direction of a negatively charged particle is towards the particle itself. So if you can see it here, that the electric field is directed towards the negative charge. And if that is a positive charged particle, then the electric field is going away from the particle. So that is our convention in terms of direction. So this one is a vector representation wherein the arrows represents the vector of the electric field. And these are the how the lines are represented. So these are the lines of force, and at the same time these are the magnetic field lines. Again, these are magnetic field lines, and that magnetic field lines No, not magnetic field. Electric field lines is directed towards the negatively charged particle. For a positively charged particle, again, it is directed away from the charge. And again, the intensity of the electric field would depend on the distance from that charged particle. So the nearer let us say a test object, say we have here a positive charge, the nearer it is to the charge, to the one having to the charge in that we are talking about, the greater also is the electric field. So if the charge is here, then we have here the greater electric field, or this proton would feel a greater electric field compared to at this position. And if it is really that here, then the discharged particle would feel a greater electric field compared to the one before it. Okay, so this is a diagram or a representation of a single charged particle, its electric field. So a representation of the electric field of this single charged particle. And we have here a representation of two charged particles. So if you could see that we are consistent with our direction of the electric field, that positive charges, the electric field is going out of its center. And we have negative charges, the electric field is going towards its particle. Now, notice how the two connects. So from positive to the negative. So that would tell you there is a connection between electric fields of the two charged particles, meaning there is an attractive force, meaning they are attracting to each other. And then you can see it from here. So notice that the electric field is like this, and notice how it bends. So meaning there is a disturbance in the field as it feels the presence of another charged particle. So their fields, the disturbance in their fields, uh, somehow their fields connect to each other. So again, when there is a disturbance in the electric field, the electric fields tend to somehow bend. So you could really see that there is really a disturbance. So if there's another presence of a charged particle, that certain charged particle would feel its presence by a disturbance in its electric field direction. So this one also could connect to that one, but however it's already farther, and this one also is already farther. Now if you observe, there are more electric fields here, therefore there is a greater force of attraction at this point than at this point right here. So the more electric fields, the more is the force of attraction, or the greater is the force of attraction. And this one is it's an arrangement of electric fields of two plates of opposite charges. So notice, because um, the the charges are arranged in such a way that they are uniformly arranged, so you would expect that their electric fields are also uniformly arranged. And if you are asking me of magnitude, so the magnitude of electric field here is just the same as the magnitude of electric field here, and so is here. So meaning to say, electric field at this uh, area right here are all the same or constant. Follow? Next, so the electric field concept helps us understand not only the forces between isolated stationary charged bodies, but also what happens when charges move. So when there is a moving charge, the movement is communicated to the neighboring charges in a form of field disturbance. So again, the field disturbance is when its field direction somehow changes, or there's a bending of the direction of the electric field. So that disturbance emanates from an accelerating charge body at the speed of light. So when there is a moving charge, that moving charge somehow disturbs the electric field of its surrounding. So there's a disturbance, and that disturbance is emanated until it reaches another charged particle. So it's like a water wave when you see a still water and you are going to throw stone or a rock pebble on it, you would see the waves. And in this one also, so electric field somehow emanates the disturbance into its area if that is moving. So if there's a moving charged body and that is moving at the speed of light. Now, there is what we call electric shielding. So when we say yes, there is a difference between electric fields and gravitational fields because electric fields can be shielded by various materials, whereas gravitational field, no matter how you try to block uh, the field, that gravitational field I mean that object that you are blocking has no effect on the gravitational field on the one after that object that blocks the gravitational field. So, however, in electric field, there's what we call shielding, meaning we can uh, we can try to shield electric field. We can try to cover such that at the other end of that covering, there is no more electric field. So what happens to this car is that the car is somehow shielded. I mean, the person is somehow shielded with the surface of the car. And that's why even if there is somehow an artificial lightning strike here or a spark or an ionization of the air in here, you notice that the person is not affected. Notice that the person is not electrocuted because the person inside a car is protected by the shielding effect. So somehow this metal right here becomes the shield, meaning to say inside this car there is no electric field. Electric field is zero inside the car. But outside the car there are electrons here. So somehow the electrons, as you can see it from here, somehow the charged particles is just circling around the object. And inside that object has a zero electric field. So E is equal to zero at this particular inside of this shape. Okay. So that is what we meant by shielding effect. So metal can completely shield an electric field. So during a lightning strike, it would be safe if you are inside a car or if you are inside your house. So do not try to, let us say, walk around when somehow there is a storm coming, and then during the storm there will always be some lightning strikes and discharges to the ground. So better be inside a house or inside a car to be safe. Now, looking at this diagram right here, so this is how charged particles in a metal arrange itself. So notice, because these are the same charged particles, so there is a repulsive force. So notice that they will be moving away from each other, and that um, if there is a certain charged particle here in the inside, it will be repelled by the two objects right here. So somehow everything will always line up on the outside of the surface of the object. And notice also that there is a crowding at some pointed areas or curved areas in a metal surface. So notice it here. And notice here that if it is not really that sharp, then there's no crowding. Now, let us say if we have here a cloud right here which has a negatively charged side. So what will happen is that positive and negative are attracted with each other. So there's a greater electric force, and that electric force generates an electric field. So the greater is the electric field, the more likely that this electron will transfer to that position right there. Meaning to say, during a lightning strike, a lightning would always search for a part of the object that is pointed. That's why we have lightning rods to prevent, let us say, the lightning to strike at any part of the ground, rather than instead of going to the ground, it will somehow be sucked up into the lightning rod, because the lightning rod is designed to be some pointed material or metal object. So lightning strike will prefer at this position. Why? Because there are more charges here. More charges, more electric force, more electric field. And then that's it. So most likely, lightning strike would always be somehow directed to a certain object that is pointed. And it should be metal. Okay. And then Gauss law for electric field. So this is just another way of telling us the number of electric fields as the number of charged particle increases. So this will just tell us, or this is another way of looking at the number of electric fields as the net charge is increased. So if we have here a single proton, we only have here, let us say, 12 electric fields. So this is just an example. So 12 electric fields, and say if we have two charged particle, so we have 12 and 12, and then since there is a repulsive force, so the charges or the electric fields of each charged particle tend to repel. They will not be connected, so they tend to be directed towards the outside or to the surface of the object. And so as with this one, by the way, this is what we call a Gaussian surface. A Gaussian surface, meaning to say this is just an imaginary surface wherein we are trying to quantify the number of electric fields that tries to go out of that Gaussian field or Gaussian surface. So the as the number of charges increase, there will be more electric fields that will try to get out of that Gaussian surface. And again, if we have now 4 electric charges, then we will have 48 field lines. So this is also similar to how you would understand the shielding effect, because of the center, because of the repulsive force, that is a zero electric field. That is because charged particles of the same charge tend to move away from each other. So at this point, their electric fields are somehow directed to the outside. So making this or leaving this area right here a zero electric field. And we have here electric potential. So if you can still remember gravitational potential energy, so in other words, potential energy. So if this is Earth and this is an object right here, we try to put something, let us say a very massive object on top of Earth, and let us say we are here standing. Now this object right here seems to have a potential energy, somehow a stored energy, such that when you try to release this one, this person right here could really feel the energy as it hits the head of the person. So meaning to say, anything that is away from Earth or at a certain height from Earth has potential energy. And then the farther it is, the greater also is the potential energy. That is because it has a formula. Potential energy is equal to mass times gravity times height, or the weight of the object times height. So the farther the object from Earth, the greater is the potential, meaning to say the harder it tends to hit the ground if it is farther. You follow? So meaning to say, because of the force of attraction, the farther it is, the more likely it will hit harder on the ground than it is when it is closer at this position right here. So again, there is somehow a potential, an energy stored, a potential of hurting the ground or hurting your head as soon as this one is released. So the same with charged particles. So since this one is, there is a repulsive force between these charges here, let us say A, and charged particle B here. So there's a repulsive force. Now when you try to push this one, this charged particle to this position right here, you would feel difficulty in pushing that one. Why? Because there will be a resistance because there is a repulsive force. It's like pushing a spring to that direction. So when you try to push the string to that direction, you could feel the difficulty in pushing that one. And at this particular moment, I mean position now, if you try to put something right here, let us say a rock, then release the spring, then you would see that the rock will be pushed to that direction right there, meaning there is a potential of pushing something to that direction. Do you follow? And so with our electric charges, as you push the positive particle to that direction, at that position, there is a potential that this particle right here, upon release, will move to that direction. Because there is again a repulsive force between the two. So as you push it towards here, there the greater is the repulsive force. Because as we know that uh, electric force depends on the distance between the two charged particles. So that is what we call uh, this is now, or this one now has gained, just like this object right here, or this rock right here, as you move it away from earth, it gains potential energy. This one also gains potential electric potential energy. So that is what we mean by here, electric potential energy. So in terms of equations, so electric potential is different from electric potential energy. Simply, electric potential is just potential energy per amount of charged particle. So let us say a certain charged particle, let us say, gains, um, let us say, three charged particle has a, let us say, three positive particle has a potential energy of, let us say, 30. That means the electric potential, because electric potential is energy per number of charge, so that means the electric potential is 10. Do you follow? So the unit for electric potential is joules, and then the unit for charge is coulomb. So we have your joule per coulomb, or that is equivalent to 1 volt. So meaning to say, the unit for electric potential is in terms of voltage, and the unit for electric potential energy is in terms of joules. So that is always the unit for energy, that is in terms of joules. So see the difference? When we say electric potential, the unit is volts. And when we say electric potential energy, in terms of energy, the unit is always joules. So when we say energy, the unit is joules. So that would tell us that for every 1 volt, there is 1 joule per coulomb of electron. So you divide it with the amount of charges present. So it is like, let us say, 10 of you, 10 of you has 100 pesos each. So 10 has 100 pesos each. So the total energy all of you has, or let us say the total money all of you has, is 1,000. But each of you, in terms of electric potential, each of you has 100 pesos per person. So that is the difference between electric potential and electric potential energy. Meaning to say, that is money per person, or energy per coulomb, or energy per amount of charged particle. You follow? Now, if we have here a certain charge object with lots of charges, and we also have here two charged particles, one having less number of charged particle compared to the other one. So A has less charged particle compared to B. Now we are asked, now they are of the same distance. They are of the same distance. The question now is, which one has greater potential, electric potential? So using the equation, we have here, this one has more potential energy because it has more charges. Meaning to say, there is more repulsion here than here, because this one has only less number of particles. So more repulsion, meaning more energy stored. So greater electric potential energy However, they also have greater number of particles. So we have greater number over greater number compared to this one. So meaning this one has less energy, although they have less energy, that's because they have less number of charges. So both of them has equal electric potential. So if we put numbers here, let us say we have here 100 joules divided by the number of charge, let us say 10 uh, particles, or let us say 10 column. And here we have, let us say, 10 joule over 1 particle. So if you divide them, both of them will have an answer of 10. So meaning its electric potential is just the same, although they don't have the same number of particles in electric and potential energy. So again, both of them, both of these A and B here, charged particles, have the same or equal electric potential. So again, in terms of equation, the more we push the object, the greater also is the force, the repulsive force between them. So in terms of electric field, this is our formula. Electric field is equal to force divided by Q. And then if we rearrange that, we will have force is equals to number of charge times the electric field. So when we try to push this one, we are exerting force, we are doing work. So when we say work, that is force times distance. And work is just the how much work you exert is also how much energy you spend. So we represent potential energy with delta UE, or that is the potential energy. So the formula for potential energy is force times distance. And then if we have force here, Q electric field, so we now have the formula Q electric field times distance. And so in terms of electric potential energy, we have electric potential energy formula a while ago, which is delta V is equals to potential energy divided by the number of charges. So we insert, or we change the formula for potential energy into this formula right there. In other words, we are solving for electric potential in terms of Q, electric field, and distance divided by Q. So that's why we have this one. So we now have this to that position, and this one here at the denominator. So this is now our another equation for, we simplify this one. We have Q divided by Q is cancelled. So we have electric field times the distance is equal to electric potential. So this is our another formula for electric potential. We have here the, our earlier formula, which is potential energy divided by the number of charge. And then we also have in terms of electric field and distance. You follow? So as an example, so imagine moving a proton from a negative plate to the positive plate of a parallel plate arrangement. So this is our parallel plate. We have the positive plate here and the negative plate. So imagine moving this proton towards the positive plate. So you could really feel the repulsion, the repulsive force increases as it moves to the positive plate. So the plates are 1.5 centimeter apart, and the electric field is uniform with a magnitude of 1500 Newton per coulomb. So we are now asked of electric potential energy. So electric potential energy, or the delta U. And then letter B, we are asked of the electric potential difference, or the delta V. And then we are asked of the speed, or the V, of this charged particle, this proton. As you release it, since there is a repulsive force between the positive plate and the proton, so it will move to that direction. So question now is how fast will it be moving? So that is letter C. So these are our given. This is our electric field, 1,500 Newton per coulomb. This is the charge of proton in terms of coulomb, and this is also the mass of proton in terms of kilogram. And then we have the distance between them, which is 1.5 times 10 to the negative 2 meters now. So since we are moving decimal places, it is now changed to meters instead of centimeters. So the standard is it should be in terms of meters. So again, for the formula U, delta U is equal to Q ED. So that is coming from this formula right here, our previous formula. So the value for the charge is 1.6 times 10 to the negative 19, then electric field, and in the distance. So the answer is, or the potential energy, or the electron would feel, or the potential energy has a potential of moving to that direction. So it has a potential energy of 3.60 times 10 to the negative 18 joule. Next is the potential difference, or the delta V, or the voltage. So we have here the potential energy, which is we already computed it here, and the charge of proton, which is this one, which is just given. So the answer is around 22.5 volts. So imagine a car battery has only 12 volts. So imagine how great is that voltage, or the potential difference, and it only has one proton. So that only has that is the energy of a single proton. That is 22.5 volts. So in terms of if we will go back to here, we can say that in terms of voltage, this one has a 0 volt potential, and this one right here is 22 positive 22.5 volts. You follow? So the potential difference between them is 22.5 volts. Next, in terms of velocity, so we could use kinetic energy formula. So kinetic energy is equal to 1/2 mv squared. And since as you release the charged particle, it has a potential energy of this value right here. So that is the potential energy. And that, or all of those potential energy, is converted into kinetic energy. So meaning potential energy is equal to the kinetic energy. So this one right now here will be 3.6 times 10 to the 18, and we will consider the mass of the proton, so we can solve for the velocity. So the formula now, since it has a square, so we invoke square root. So that is 2 times potential energy divided by the mass, and the answer is around that much. So if you could see, this is around 65,000 65,700 meters per second. So that is a very fast velocity. Okay. Next, accelerating X-rays, or creating X-ray. Now this is how X-ray happens. We have two plates again, negative plate and a positive plate. And what happened is that as voltage is as you connect this one to a voltage source, let us say this one it could be a battery, or this one could be an AC source, alternating current source. So the plates here, which is positive and negative, could create an attractive force, and could also create an electric field between them. Now, so the X-ray machines for diagnosing hidden dental problems. So electrons are accelerated through through electric potential difference of 25,000 volts, meaning to say the potential difference between them is around 25 kilovolts or 25,000 volts. And as this electron hits because of the greater attraction, because of the greater electric field and voltage, some of the electrons here will be pulled towards the positive plate, and as it hits the positive plate, it emits X-rays. So when the electrons hit the positive plate, their kinetic energy is converted into a photon. So because of this high or fast moving particle or high energy particle hitting this positive plate, as it hits the positive plate, it releases or it creates an X-ray photon. And this photon now is used to somehow penetrate into the skin or into organs or tissues so that doctors can see what's inside organs and tissues. And then suppose a single electron's kinetic energy is distributed equally among 5 X-ray photons. So how much energy would one photon have? So we are talking about energy, so delta U. So how much delta U does one proton has? So one proton, delta U for a single proton. So we are only given with the charge of the proton and the voltage. So we can compute for the potential energy. So using this formula, potential energy is around 4 times 10 to the 15. So that is just a very small number since it is a negative 15. So that is just a very small energy. And that energy given to us to a single electron, as that energy is transferred into photons, into 5 photons, uh, we are asked of how much energy does one photon have. So this is the energy for that single electron. We're talking about a single, yes, a single electron. And then since it releases 5 photons per electron, so we will just divide this one with 5. So that's why we have this one and divide it with 5. So that will now be equal to 8.0 times 10 to the negative 16 joules per photon. Although 5 photons will have 4.0 times 10 to the negative 15 joules. So again, that's just a very small energy if we are going to look at it. Okay, the last topic would be capacitance. So when we say capacitance, um, capacitance has something to do with capacitor. So what is a capacitor? So a capacitor is just a plate, a parallel metal plates. So these are two metal plates. We have here this plate right here and this another plate right here. So that is a capacitor. So a capacitor is just, initially it is a neutral plate, meaning the number of protons equals the number of electrons initially, if we did not yet connect this one to the battery or to the voltage source. So that is the same as here also, plus, 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 and so on. So all of them is neutral. Now as you connect this one, so that is separated by a certain distance. So the two plates again is separated by a certain distance between them. So connect this one to a battery. So what happens is that a battery is an object that has a very large charge separation. Meaning to say, consider this part right here as all protons that are crowding or that are grouping at each other. And then we also have electrons here that are grouping at this part of the terminal, and then they are not connected with each other. Meaning to say, this electron cannot just pass through that positive to the positive terminal. So they cannot pass through. So as soon as you connect it with another, with a wire, so this electron tends to pass this way rather than go through the battery. You follow? So let's discuss first the positive part. Now this part right here has more positive charge particle, and this one right here is neutral. So what will happen is that the positive charge particle, this terminal, will try to attract this electron right here. So the electron of this neutral plate. So what happened is that if it somehow pulls or attracts all the positive the negative charges, so what is left on this plate is a positively charged particle. And the same is true with this part right here. So this part right here is or has a lot of negative charges right here, and this one, which is initially neutral, this one here is initially neutral. What happened is that this one is neutral and this one has more electrons here. So what happens is that it's like a door, a room full of students. Let us say 500 students fitted into a single door at school, a single room at school. So as soon as you open the door, as soon as you give a pathway, electrons would tend to somehow run outside of the very fully packed classroom. So as they move, then they try to distribute themselves here, leaving this plate a more negatively charged plate. And aside from that, we have here a positive plate. This positive plate also attracts the electrons here. So meaning to say, it somehow pulls the electron from the battery. Aside from electrons going out by themselves, there is also a certain pull by these protons right here. So somehow they will really get out of that positive terminal. And since they cannot jump off to the other plate, it will stay here. The negative electrons will stay here, the negatively charged object. So leaving this one a positively charged plate and this one a negatively charged plate. Do you follow? So there is just a movement of plate because of the attractive force, wherein there was a pathway provided. Do you follow? So this is now a capacitor. So basically this is a capacitor, and as they observe, as they, let us say, they tried 3 volts, 3 volts, they also tried 6 volts, and they also tried 12 volts. So they observed that as you increase the voltage, as the voltage is increased, the number of charges on the plates also increases. So there is a direct proportionality relationship between the voltage and the number of charge stored in these capacitor plates. So if we want to know the constant, so the constant of proportionality, which is C, is now equal to Q divided by V. And DC and C right here is what we call the capacitance. So capacitance is like the capacity or the max, let us say the carrying capacity. So how much charges can it carry with respect to voltage and the number of charge. So how much charges, how much protons and electrons can it carry? And that is what we refer by capacitance. And that is in terms of coulomb per voltage. And that coulomb per voltage is just equal to a farad. So 1 farad is equal to 1 coulomb per voltage. So capacitance represents the amount of charge stored per volt. So when a capacitor has large capacitance, it holds large amount of charge per volt. So if this one has a large capacity, it could hold large charges, then it will have large capacitance. And if it has only less capacitance, then it will only, or it can only hold less charges per volt. So if you look at it, so if you have a very wide capacitor plates, then it could hold more. So its capacitance increases. Do you follow? So, so capacitance depends on the size or the shape of our plates and the spacing. So in terms of equation, in terms of electric field, this is how electric field is described within the plates of the capacitor. So again, electric field is the field, is katong when we say field, that is the how many electric field lines are present in this capacity. I mean these two parallel plates. And so we have this formula previously, and then if we change E with this 1. So we will have this one, and since we have distance, so this is the initially E, and we have here the distance, which is the original formula, divided by area. And if we place this one in our formula for capacitance, so if we insert this formula here in our voltage, so the result will be this one. And 1 over 4 pi k, this one right here, is equivalent to EO. And the EO value is that one, or that is the permittivity of free space. That means that the space between the two plates, how permittive is it? How it could permit one electron to go through from the negative to positive. So that is what it meant by permittivity constant. So different dielectric. So we call the material here in between as dielectric material. So different dielectric material offers different permittivity. So the formula now for our capacitance is this one. So as an example, so what would be the plate area of an air field? So this is our dielectric material, the air. So we have a 1 farad parallel plate capacitor separated by 1 millimeter. So question is, would it be realistic to build a capacitor, a 1 farad capacitor separated by a 1 millimeter distance? And how much is the area between the plates, or how much is the area of the plates? So we have here the two plates. So the area should be, let us say, this is the length, or this is the width, and this is the length. So what is the area of our parallel plates capacitor here? So given with the formula previously, this formula right here, so for solve for area, so we have this formula right here. And the value for C is 1 farad. And the value for D, or the distance, is 1 times 10 to the negative 3 meters, since this one is in millimeter. And then the value of the permittivity constant, so the answer would be 1.1 times 10 to the negative 8 square meter. Now if you try to look at this one, this is around 1 million, no, not 1, that's 110 million. 110 million square meters. So that's a very large area, and it would not be realistic because it would be somehow as big as, let us say, Lapu-Lapu City, I think. I'm not sure. So that is not anymore a realistic capacitor. So again, it's only 1 farad, and that is already as big as Lapu-Lapu. I mean, the area is already as big as, I think, Lapu-Lapu, or let us say 5 barangays of Lapu-Lapu. So that is around 100 square kilometers. So that's even bigger than, I think, Lapu-Lapu City. Okay. Although, however, there is already a new technologies arising wherein they are now able to create a compact high capacity capacitor, so which we will not be discussing. So that will be all for today. So we are able to discuss. We are almost done with our prelim coverage. So here is our prelim coverage. So we are done with